Here we go.
And you're live.
Lovely. All right. Good morning, everybody. Put a thumbs up in the chat if you can see and hear me, just to make double, triple sure. Good morning. If you can see and hear me, go ahead and put a thumbs up in the chat, just to be double, triple sure. Awesome. I'm seeing thumbs up. And I've got a lot of content to share with you today. So I'm going to just get started. If we haven't met yet, hello. My name is Andrew Adams, and this is a presentation on Project SAROS. Project SAROS is about chasing solar eclipses with rockets, and we're just going to jump right in. You may remember some of these slides from last year. So first, if we haven't met yet, I'm from Durham, North Carolina, and I now live in Seattle, Washington. I did high school and collegiate rocket teams starting 2012 through 2020. I've been doing rocketry for a little over 10 years now. I got my L3 in March of 2022. I'm now the secretary of the Washington Aerospace Club, which is a local group out here in Seattle. And I love to hike and occasionally sing. Here's a few pictures from my past experience. This was the most major experience for my first rocket team in 2013. We did the NASA Student Launch Initiative, and this was our little group of 8. Homer Hickam showed up to that launch and signed our nose cone, and that pretty much sealed the deal. This is a picture from when the first time I led the MIT rocket team, 2017. We went to Spaceport America Cup. We got second place. This was the first Spaceport America Cup. It used to be IREC, but this was another huge experience. Now I'm a fluids engineer at Blue Origin. My path through rocketry really traces the path into aerospace engineering on a one-to-one line. And then this is a picture of me being silly and hiking the enchantments as a day hike. With not pictured, but we did this with a bunch of friends. Some of whom were also at BlackRock for the first Eclipse launch. But I'm getting ahead of myself. So I'm going to go back about a year to when I released a video called "I Have a Cosmic Deadline." This was my video kicking off Project SAROS and really establishing the terms of the project. And so my goals for this project were threefold. The first was exactly what I've been talking about: use rockets to get video of the next 2 U.S. solar eclipses from the air. The second was to share and document this process on YouTube, to document it for myself, but also to inspire other people. And 3, this is a hobby project. I want to have fun with it. And if I'm not really having fun with it, then either a rocket has crashed or I'm doing something wrong. And I will accept rockets crashing as part of the project. That's just kind of part of rocketry, right? And so the whole part of the project was this leap of faith that the annular eclipse, where the moon shadow is really soft. There's no unlike a total eclipse, an annular eclipse doesn't fully cover the sun. It leaves a what people like to call a ring of fire of the sun. But the moon shadow, the penumbra, the softer shadow, gets projected onto the Earth anyway. And I thought if I get high enough, if I combine the moon shadow on the landscape with an example like this is from a Jim Jarvis flight to 142,000 feet, we'd be able to get incredible imagery. But this was a topic of some debate. I talked to a couple of people very early in the project, and they were convinced that we weren't going to see the moon shadow. I was convinced that if we get high enough, we should have enough horizon to detect it. We may need to get the light level just right to really be able to see it. And that might have to happen in post in some photographs, but we could do it. But this was really the kernel of it. And the annular eclipse was special because the path goes over BlackRock, and BlackRock is well established as the premier launch site for amateur rocketry, save maybe Spaceport America and Friends of Amateur Rocketry, but neither of those two places were on the path of annularity. What's special? So for the annular eclipse, again, the moon doesn't fully cover the sun, but you have to be on this path in order to see the moon fully go inside the solar disk and like leave that ring of fire. If you are still within the moon's shadow, but you're not on this path, you'll see a partial eclipse and you'll end up seeing a crescent of sun as it is blocked by the moon. So last year, I talked a lot about test flights, and I wanted to do a lot of test flights because this was a flight that was pretty far out of my range. So I'm just going to recap these test flights really quickly for you.
Okay, so after that test, we increased the amount of black powder, almost doubling it for the flight.
Actually, real quick,
however,
do
it
you hear
still
the
wasn't
sound on the
quite
video
enough,
or no?
and instead we hot staged. Next time, we'll leave more time for stage testing, double checking the.
Put in the chat if you heard sound on the video or not really. I didn't have a chance to check this, so we're just gonna check it live. Oh, you did hear sound on the video. Oh, that is honestly awesome. I did not expect that at all. I was expecting them all to be muted. Okay, so I'll keep that in mind. So this was the first test flight where I collaborated with my dear friend Joe Barnard, and we did a two-stage flight. We were at a very similar point in development. Oops. We were at a very similar point in our rocketry lives, and we decided to do a two-stage project together. And so this taught us a bunch of things. We tried to do a like piston-based separation system for this project, which did not end up working, and the backup was hot staging. But other than that, this worked really, really well. Everything came back in the right number of pieces, except the one camera that we accidentally torched with the hot staging. And so we learned a whole bunch from this flight. The second flight was the first time that I flew a 360 camera, and so I'm also going to mute this one. Most of them will be muted, but this flight was really about figuring out how to mount a 360 camera undershoot. I knew early on that most of the time in flight for a flight to 90,000 feet or so is going to be undershoot. So I figured the best way to have the 360 camera was to deploy it with the chutes, and then I wouldn't have to worry about it sticking outside the rocket. So we developed these 3D printed camera cases that worked pretty well. If a little bit bulky, they ended up being throughout the project. I ended up slimming down this 3D printed camera case pretty significantly. We should be coming up on the flight here shortly, I hope. I'm just going to skip ahead a little bit. So we got these views from the 360 camera in flight. Half of it got covered with soot from the black powder charges. But other than that, we got this was a really good test flight. Like we were able to see the entire horizon. I was able to learn the software pretty well. And I learned some lessons going forward about the necessity of protecting these darn things from soot. So that was the second test flight. Then the third test flight did not go well. The third test flight ended up being a very interesting failure. I don't think I have any more on that test flight. No, I don't. So I'll just explain it briefly here. Basically, this is potentially what happens when you leave the igniter at the bottom of the solid rocket motor. The night before this flight, we developed some custom igniters that we wanted to try out, but since the motor I had was a moon burner, it couldn't get both through the nozzle and then like kind of around the corner. And then so it got caught on that corner. And at this point, the 360 cameras were running on the rocket, and we knew that they didn't have a ton of life. And so we were like, okay, we're going to try it at the bottom of the solid rocket motor. It should be okay because it's a big igniter and it should light enough propellant to like start pressurization. And we were wrong in that, and instead it burnt through the entire motor like an end burner. Since it was the moon burner, those also tend to be really slow burning propellants. This was an I-125, and it was a 5-grain motor. So the propellant burned really, really slow, and it just kind of sat there on the pad burning um, the entire time, which was it was weird. It was super weird. But luckily, I got to keep the electronics and the cameras and the shoots. So it wasn't a total loss, but it was enough that I had to move on to the next rocket, especially after I spent several weeks putting together the video for this one. So we moved on to Tycho 1. Tycho is the name of the Eclipse rocket, and this was the first iteration. Instead of doing those 7 test flights and like iterating up, I skipped straight to the Eclipse prototype because at this point it's like March, and I wanted to really get a sense of. I needed to learn a whole bunch of things. So this was a full-size prototype. But it was underpowered. The whole point was to the whole point was to get used to the size of the thing. We had Eclipse-like avionics, we had Eclipse-like camera setup, and a ton of deployment testing. I did 5 sets of ground tests, 5 sets of ground tests for the sustainer in particular to get the recovery scheme right. I wanted to be able to reuse the booster interstage section, so where the sustainer meets the booster was going to be hopefully the exact same hardware, 1-to-1. The stage separation. This was the first time I did. It was another piston-based stage separation system, except instead of it being a like McMaster piston that you put a black powder in that keeps it really, really well contained and focuses it to like a single piston rod, it was more of a it was like a full diameter piston where a piece of coupler and a bulkhead slid within the body tube, and then the sustainer rode along on that. It was single step dual deploy for the sustainer in order to deploy the cameras and the shoots. This was in an effort to reduce the recovery volume at the cost of complexity. I did have tender descenders on this thing. That's also part of why we needed 5 ground tests to get it right. And this was my first minimum diameter build, which was pretty significant. The booster had a bunch of reused hardware from my L3, so the fin can was just drag and dropped over onto this new rocket. But the upper 2/3 of the booster was brand new, and then the sustainer was fully brand new. And then lots of operations practice. So like, how does this rocket feel to actually launch? If I am like on Eclipse Day, like operations are going to be the most important thing, and I needed practice at scale. So I built this over the course of about 3 months, March to June, and I flew it at Brothers, Oregon, at OROC on June 25th. And I flew it on an L1115 to a K1085 for an estimated 18,000 feet. And since we do have sound, you get sound on this one. So this is going to be super fun.
Come on!
Okay, here we go.
I see smoke.
Yes! Yes! Good boost. Good. Set. Look at that. Set. Wait. Oh, that's a smoke charge. Okay. Oh! No way! No way! Oh my god!
Yeah, that's pretty cool. Also, Robin, I'll get to your question. So at this point, the sustainer lit. We're getting telemetry from both the sustainer and the booster.
Oh, no.
But shortly after that,
No.
the booster failed to deploy its shoots.
Come on, booster!
Well,
All right.
that wasn't quite as fun. However, the sustainer did deploy its chutes. Let's skip ahead. Here we go. So the booster did crater, which is a bummer. But the sustainer did deploy its chutes, and we were able to recover it within the hour. So we actually ended up splitting up because we were 24 hours behind schedule, and me and my girlfriend, who you also saw in that video, it had a place to. We had a concert to go to that night, so it was. And so the folks at OROC were extremely generous, and like were able to go and pick up the sustainer, while me and one of the other folks at OROC picked up the booster. And while Janice picked up the campsite with another person from OROC, so we were flying. But so the sustainer worked, which was a good proof of concept. However, the recovery did deploy early. I could see, I don't think I put the data in here, but the main deployed at apogee by accident, which was a little bit of a bummer, and it tangled pretty significantly. And this ended up driving a change to dual set, dual deploy for the next iteration. And the booster chute since the booster chute didn't deploy, that reusable section of booster I was hoping to use just was in the ground, and we got it out of the ground, but I couldn't use it anymore. But this was overall a pretty successful flight test. Well, half of it was very successful, and half of it was medium successful. So at this point, I have a bunch of summer plans with my family, and I need to make the video for this. And so by the time I get to actually building the next rocket, there's only 2 months left. It is August 12th, and I have a whole bunch of parts on the table, but I have to rebuild the entire thing. I can't reuse the sustainer because it was only my first minimum diameter build, and I guess I never stated it, but the goal for Tycho 2 for the Eclipse was 90,000 feet, 90,000 feet. And so the sustainer just really was not built for the Mach 3 and high altitude environment like that. So I had to rebuild the sustainer anyway. And since I lost the reusable stuff, I needed to rebuild everything. I only had one big test window. Express and balls are in September. But if I did that and crashed the rocket, I would not have enough time to rebuild it after. I'd have less than a month, because I think I was targeting like maybe September 17th, and the Eclipse is October 14th. So I had a choice to make. Do I descope to like a single stage situation similar to my L3, or do I full send? Because an Eclipse is a once in a generation kind of opportunity. And I chose the full send option. Because I thought we could do it. And so this is a 14-foot, 3-inch tall, absolute monster, Tycho 2. It is a 4-inch diameter booster. It's a 3-inch diameter sustainer, both minimum diameter builds. The booster weighed in at 49 pounds. The sustainer weighed in at 26 for a grand total of 75. The motors that I decided to fly were the N5800 to the M2150. The N5800 is the motor that many of us fear, and then the M2150 was a 6-grain CTI 75 that I could get my hands on. I thought about flying the IMAX, but that seemed a little bit out of range. Plus, since Tripoli does a lot of the launches out of Black Rock, and Tripoli's relationship with the BLM was really, really important for getting all the permits for this. You're basically flying under Tripoli rules without it being a Tripoli sanctioned launch. And they have a class 3 waiver requirement at 100,000 feet. So I chose a motor to keep myself squarely under that, because yeah, exactly. Full send is the choice. And then since the single deploy didn't work, both of these stages were dual set, dual deploy. I tried to make it nice and compact as best I could, but they were both dual set, dual deploy because I was not messing around. My strategy for these builds was to take every technique I knew and like give myself plenty of mass to work with, right? So for so I did tip to tip layups on these, and I did 6 plies of fiberglass on each one. I really wasn't, as long as the rocket was going to have a stable flight, I really didn't care about how much mass it was going to take to do it. It's a full send, but like that's the one reasonable part of this full send. So on August 12th, this is what the garage looked like. There are a bunch of tubes. There's a bunch of tubes. There's a bunch of fin material. Most of the motor stuff is in. The N5800 isn't even in yet. And then by October 1st, we had built pretty much the whole thing. And we were on to our first round of ground testing. I'm going to talk about deployment charges a little bit later, but it took two rounds of ground testing. We ended up shifting from the vinyl tube charges onto the more Jim Jarvis style, the long copper tube charges, but we'll get there. Then by October 12th, we'd run 2 rounds of ground tests, and we were out on the playa. For almost everybody in our group, this was our first time at Black Rock, which was positively magical. We'd done a lot of research. We were familiar with the rules of Black Rock, like leave no trace, turn it up to 11. And yeah, so we went out to Black Rock October 12th. I wanted to extra share this clip.
Survive. The sustainer.
That's the wrong clip. Let me find it real quick because it is way too awesome not to share. This one doesn't have any sound. I just wanted to share this this Star Trail clip or the Star time lapse clip in particular, taken by one Joe Barnard, is one of my favorite clips from the launch site, and that was our first night. That was our first experience at Black Rock, so we were ready for something quite amazing. And so we put it together, we got it on the rail, and I'm just gonna skip straight to the launch. Let's do it. Actually, I'm gonna shift the sharing around. Give me I'm going to take 15 seconds and shift to the actual launch clip. Since we have sound, I'm just going to change tabs real quick. And I'm going to go play it out from just the launch. We had some pad issues that I'll also get into later. So this was about 20 minutes after we were planning to. All right, cool. We're gonna go back to right here. All right. I'm getting 5x5 and we have a screen. Thank you for your help, Todd. We are back and now we are going to actually watch the launch clip. All right. No more waiting.
Ready. All right, everyone quiet. All right, launch pad armed. Going once again. 5, 4, 3, 2, 1, launch. There it is. There it goes! Oh, what the heck? Okay, everyone really quiet.
We're just going to let it play out.
Booster lost telemetry 999.
Your sustainer?
Sustainer says 300 meters. Where's the sustainer? Sustainer's coming down.
Quiet. It's coming in. There it is.
Where?
I see something falling. Got it. I hear that way. Oh, that's an impact.
There's an impact, but I don't see depth.
All right. So, not the outcome you want. So we're going to look at what the heck happened. So this was the tracking shot that Joe got. We're going to get a detail shot of it soon. This is about 4x slow-mo. You can see the ascent is like pretty good. It like kicks over at an angle, but for the most part, we're chilling. We're stable. We're doing great. And then whoop, something happens. So actually, the next shot is the same shot, but I zoomed in and slowed it down. So we can see it bends a lot, and then fails. I'm going to show that one more time just to make sure everybody saw it. Bends, breaks. So this is shot at 120 frames per second, and that event happened in about like the main event happened in probably like 12 frames, and it was all done at about 40 frames. So this was an extremely quick event. So this is an energy profile. Shout out Max Fagan for making these graphs based on the telemega data. We were able to recover all of both of the primary flight computers. So we were able to get a lot of the data back. The black dotted line is the simulation. This is velocity on the x-axis and height on the y-axis. So we go faster, and then at about 550 meters per second and about 760 meters above the ground, something happens and it breaks and it very quickly slows down. And then our estimates kind of fall apart after that event. I believe that if I remember correctly, it was primarily accelerometer integration that was used to calculate these. And then the accelerometer saturated really badly at this point. So our estimates are a little bad after that, but it's easy to see the speed and the height at which this thing failed. So what actually happened at this frame, we can see the sustainer fin can failed first due to that high bend angle, and we did a little bit more data processing, and we saw that high bend angle, but we actually maintained a pretty significant angle of attack between the sustainer and the booster. So this plot is of the relative tilt angle. This is the sustainer tilt minus the booster tilt. It measures, so if they're tilted slightly differently, it measures this angle, right? So we're measuring the relative difference between the two. And so for almost a whole second, we were between 2 and 4 degrees. And then very quickly, when it actually starts bending over, this data becomes less useful. But this was a really cool finding. Again, shout out Max Fagan for the graphs. So a couple frames afterwards, we can see the nose cone and the recovery tube moving real quick. And at this point, the Kevlar line was still attached to the sustainer fin can. And so since it was pulling on the sustainer fin can at this point. And when it pulled on the sustainer fin can, it caused the booster to fail in bending. And so the nose cone has all the electronics for the sustainer. And so flight computers are up here. The recovery tube had the 360 cameras in it, but you can actually just barely see them. They're this black dot right here. And so both of the chutes, the main and drogue, inflated at this point. I couldn't actually see them in the footage. The main, unfortunately, is blue and gray, which don't know why we even make chutes in blue and gray, but we're going to move on. And we never found it. I'm pretty sure it's shredded. But the drogue we actually did find. Did the camera survive? We'll get there. The sustainer fin can fell out a couple of frames later, and the upper half of the booster, the upper half of the booster and the lower half of the booster stayed mostly connected, and they stayed connected enough that it actually like folded over and smacked one of the booster fins off. I don't know if I have a picture of it in here, but we actually have one of the booster fins with a paint mark on it, which was nuts, I tell you. And so after that, okay, so we go over contributing causes. So now that we know that, I am actually going to go back to that slow-mo shot one more time to just kind of like talk through it again. So watching it happen, it fails, it flips, it smacks one of the fins, and then after that, the booster restabilizes with 3 out of its 4 fins and continues out into the desert. One part that I left out of the video was we actually were able to track down the booster, and it's currently hanging out in somebody's house in Reno. I've like reached out to them and made initial contact, but I haven't been able to get the booster back yet. But they did find it. I'm also going to show the slow-mo because the slow-mo is awesome. Just as a treat, because y'all deserve it. If I can click on it because this thing is in my way.
Okay.
Please. There we go. All right. I can't have a slow-mo shot and not show it. Sorry, it's sideways. That the aspect ratio fits a little better. But yeah, this is a good shot. Tasty. Tasty. That was shot at 420 frames per second with a free fly wave. All right. So there were, actually, that's an oversight. I don't know if I put the onboard video in here. So I'm going to answer your question right now. The cameras, the 360 cameras, well, actually, nope, I lied. I'm going to come back to that. So some contributing causes to why we had that really high angle. First up was the interstage fit, which was the interstage fit. So we used the copper tape E-tape leads. So we had copper tape E-tape leads all the way down the motor, and then the aft closure was still at its full diameter. So it had to like make a knee around the aft closure. So it like goes down the side of the motor, and then it comes out at 90 degrees, and then down at 90 degrees, and then across at 90 degrees. And then you attach the igniter and put it in the motor. And so as a result, there's that section on the outside of the aft closure that you have to slide through the interstage. And so as a result of that, we ended up having, I gave the interstage kind of a loose sliding fit in order to do that. And as a result, that gave the sustainer a little bit of leeway at the top. And I thought that was okay because it had worked in the test flight. However, the big difference between the test flight and the big flight was the N5800, right? The N5800 is known for taking out minimum diameter rockets. And, I thought 30 pounds of rocket on top should be okay. And maybe it would have been if we didn't have other contributing causes, but I won't know. Excuse me. So we had a really high velocity before separation. This thing was expected to be about Mach 1.7, 1.8 at separation, which was crazy. And as a result, I've never done anything quite like that before. So I definitely underestimated what it takes to actually pull that off. We had the angled booster motor bulkhead. So that's kind of specific, but basically I think that this was responsible for creating a bend in the booster. And you can see that this was a screenshot of the high speed, and you can see that the sustainer is tilted relative to the booster, and the bend is actually in the booster. These were one of these. This red line is an 88-degree line. This blue line is a 90-degree line. So they're just ever so slightly off. And I think that also contributed to creating that really big bend angle in the first place. The last thing was the extended configuration of the launch pad, and specifically the extended configuration because the middle of the launch pad bowed out, and I have a picture of that too, in the middle or during launch. It wasn't so much that like it caused the flight to fail, but I think that if the launch rail had been stiffer, we would have started instead of like slightly off, like if the rails are a little loose, it allows the rocket to be slightly off, and that also starts up that really high bend angle. Again, like maybe if all of these things had been fixed, then we probably would have made it to SEP. Any one of them could have caused it to fail. I think it was a combination of all of these things. So I'm going to go through these in a little bit more detail, but I'm actually going to speed up a little bit. So these are some major lessons I learned in building and completing this project. So first was the interstage fit, which I talked about a little bit, making room for those copper tape E-tape leads. The interstage fit I have learned is the most important part of the staging. And if I were to do it again, I would like make sure this thing is practically hugging the sustainer, and then turn down that aft closure and find a way to like create a thrust structure in the upper half of the sustainer, just so that way those leads can make it all the way past. I think this is something that like Kip did on Mesos, for instance. I mean, he has head-end deployment, but like he also does the motor as coupler, and that I think helps a lot. But I also learned that a 3D printed interstage section works pretty well for, I would say, anything subsonic. And yeah, sustainer igniter logic. So this didn't end up being a thing, but I thought that this was pretty clever. So I wanted to, I only get one shot. This has to work. So I had redundant sustainer igniters, or I intended to have redundant sustainer igniters. And I had a pretty wide ignition window from 9 seconds to 20 seconds. 9 seconds was burnout +5. And that was, I ran some fin flutter calcs. If I lit at burnout +5, what is my max speed at an altitude? And then do my sustainer fins fail if I only have the base material to work with? And so I figured out burnout +5 was fine. And so basically anything between burnout +5 and burnout +15, which were 9 and 19 seconds respectively, I set up a rule using the telemega to allow ignition if the tilt angle is between 10 and 15 degrees. Basically, if the rocket were to, this was to catch the situation where the rocket went pretty straight, like straight enough to light the second stage, but it's tilting over a little early, say like burnout +7 seconds, it's starting to hit 10 degrees. Then it would light the motor. And this would be good because then I would be able to maximize my amount of altitude, even if while keeping the range safe. And accounting for if the rocket isn't just like absolutely perfectly laser straight. And then at 19 seconds, I say, all right, cool. If your angle is still within 15 degrees, or sorry, if your angle is within 10 degrees or 15 degrees, you can light the sustainer motor. So ideally, burnout +15, 19 seconds total, would be the time to light it. I wish I got a chance to test this out, and I probably will on the next project. So launch rail setup, we did the extended configuration. It might be a little hard to see, but at this point, the middle of the rail is like almost a whole inch out from the booster, and it bowed out because the booster was sitting kind of like this within the rails. And then when it lit the motor, it basically just kind of rode up like this, which forced the two sections of rail apart. Something else we didn't think about, we tested the launch pad. We tested the launch pad the day before launch, in the configuration we wanted, 2 parallel igniters. However, the battery was really cold on the day of, so we ended up trying everything except like doing 1 igniter instead of 2, because on the previous launch I needed 2 igniters to actually get it to go. So we just tried 1, and that extra like 20 minutes caused the 360 cameras to turn off before launch actually happened. There is onboard footage from one of the radial cameras, because one of the folks in our group just found the micro SD card, and then the up-down cameras also had it. I need to zoom. I'm running out of time. All right. Something else we did. I iterated through several different kinds of deployment charges over the course of the project. I ended up sticking with the copper tube type, ones, because basically the one thing that this have that none of the other ones have is that they have a spot where like you have a surface on the inside, a flat surface with like a high pressure, and then an area of low pressure. Like you're not relying on the whole rocket to be pressurized. You also have a reaction force from a specific spot. And I think that that's really, really critical, because I keep talking to people about high altitude deployment charges, and everybody just kind of comes up with it themselves. And like I tried the vinyl tube charges, and they were still kind of underpowered, and the copper tube charges are a little finicky. We like epoxied the caps at first, and it caused this upper one to blow out. But yeah, I think these are the way to go, just because now they like, especially if I think these are the way to go, because you get a reaction force plus the pressurization that that we all know and love. Come on, please go to the next slide. There we go. So something else I learned, that this stuff's super hard. I expected to do 7 flight tests total and a full test before. I did 4, and I did no full altitude test. I expected the videos to like be fairly easy to make. They took about half the time. I thought I wouldn't have to like put a lot of life on hold to pull it off. Nope. I did. There's a bunch. I learned a whole bunch of other stuff that I didn't go into detail on, but I am running out of time, so I'm going to skip it. So what did it actually look like? So Zyla brought a couple of balloons out there, and we launched those balloons into the Eclipse. And please let me play this clip.
That's what started it all. That's why I got my L3 in March.
Apparently I switched them, but that's fine. I'm going to skip ahead.
What we saw?
So here's the view from the balloon. Which is incredible, right? But there's something missing. There's no, like, where's the soft shadow? So it turns out that the moon's shadow is just too darn big. The penumbras like of the moon spans like thousands of miles. The folks that told me that I wouldn't see much of anything were right, but that's all right. That wasn't really the point of the thing anyway. I wanted to or at least that wasn't the reason that I started the project anyway, because I started the project because I wanted to combine these two things that I really, really love. And I'm glad I got to do it anyway. So what if the moon shadow didn't get there? We still built the thing. We still made it there. We still launched a balloon, 2 balloons, and we launched this monstrosity. And that was absolutely worth it. And I also made a movie about it. So I can link that in here if you want to learn more about what happened on this launch. It's good. I'm proud of it. So now that I only have like 4 minutes left, let's talk about the total eclipse. So first, my priorities for capturing the total eclipse. I want to capture all of totality. That's really important to me. I want to see the shadow come in, and I want to see the shadow leave. I want to resolve as much of the landscape as I can. So I want to be able to see the parts that are bright, and be able to see the parts that are very dark. And I want to do it from a rocket. But these are the 3 priorities, and they're in order, which is kind of important. One of the main challenges for doing it with a rocket is timing. So the totality of the eclipse is only about 4 minutes. And if I leave 30 seconds for launch and landing, the earliest, and I have a 6-minute flight time. So the reason for a 6-minute flight time is that is 10,000 feet plus main at apogee. The main at apogee is incredibly important. The observation time is the descent time. So if I put, and that's a 6-minute flight or 6 minutes of descent time. So if I try and put the earliest possible flight time and the latest possible flight time, that gives us our launch window. And the launch window is only 1 minute, which is stupid hard. Your igniter fails and you're screwed. The second challenge is the weather. In April, the weather is significantly worse in most places than it was last year. So last year, the 2017 eclipse had great weather, and this eclipse is looking like it's going to be a lot harder because April has a lot of clouds. South Texas has the least cloud chance, so that's where I've been prioritizing a lot of looking for a site as a result of this. The third challenge is actually resolving the entire landscape. So this is a picture from the 2017 eclipse from a balloon. You can see the dark shadow portion, but it's really hard to see the edge of the horizon. And then you can see the balloon's pretty high, so you can see the blackness above. So getting that dynamic range is going to be crucial. One way to solve this. So this is another example from an airplane where the shadow isn't as dark, but the horizon is nice and resolved. However, this also has a much the shadow is much bigger because it is like the moon shadow is really at a steep angle. And this is from a video from Carrie KH, the most elusive total eclipse of the millennium. And then another technique would be to get a composite image. So this is like many hundreds of images all laid up together to create this one. This is John Carmichael's 108. Somebody's trying to spam me. So here's the situation right now. I just finished the movie. I have a few leads on launch locations, but nothing is confirmed. I'm prioritizing South Texas area. All of these locations are 10,000 feet or above, but they're not big enough for main at apogee, which is a huge problem for observing the whole eclipse. Some of the locations are wind limited on the day of, which makes sense. And the FAA 45-day window ends February 22nd. If I really want to confirm my plans, February 10th. And so I have a few options. One is to build an ultra complex vehicle that will stay in the air for a long time and stay within the radius. Well, okay, the broadcast is still going, so I'm going to keep going. The second is to find a new launch site that can support main at apogee. Again, that 45-day window is closing. But the third option is to drop priority 3, to drop doing it from a rocket and do it from a balloon. And this is where I'm at right now. I have probably 2 weeks. If basically a landowner in the South Texas area with 8 square miles that they're willing to let me use, basically falls into my lap, I would be able to do it. But I kind of shot myself in the foot by making a video that was that long. The likelihood that I need to do a balloon to get to observe the eclipse is very, very high, which is kind of a bummer because I love rocketry, and I know all of you love rocketry too. That's why you're here. But it's more important that it's a once in a generation opportunity to see the eclipse. And we're lucky enough that we've had 3 eclipses in the last 10 years, right? And after this, the next eclipse across the US is going to be in 2045. And I think at this point I'm playing a game of logistics. And somebody says balloon and rocket. Yeah, but also that's a lot of work, and I still have a day job that I have not been doing the best at. And then plus a balloon. The nice, do I have more slides? This is exactly the same slide. I think I'm saying the things. Yeah, so the reasons to do the balloon include, one is that you don't have to worry about clouds. Two is if it's under a 4-pound payload, you don't need a NOTAM, which is pretty wild. And the combination of these things means that if there are clouds, even South Texas has about a 50% cloudiness. Like looking at the climate data from, I think his name's Jay Anderson. He like pulled together a bunch of climate data, and there's like a 50% chance of clouds, even in South Texas. So unless I go to like Mexico, and I'm not about to bring solid rocket motors into Mexico, then 50% is about as best as you get. So I'm going to the eclipse no matter what. So if I can fly a balloon through the clouds, it's also major insurance in case it is cloudy. So you deploy a balloon instead of a parachute. No, this would be only a balloon. This would be a balloon instead of a rocket. And I've sort of been coming to terms with like, this is very likely to be the answer, which is not my favorite thing. But it's another leap of faith, right? Like I didn't know if I was going to be able to see anything from the annular eclipse at all. And I did it anyway, because I wanted to observe the eclipse. I wasn't going to let maybe you won't see anything discourage me. But also in that case, the chances that I would actually be able to fly and actually be able to see the eclipse was really high. Like BlackRock was like 4 out of 5 for cloudiness. It was like 80% chance of like good weather. Plus BlackRock is an established launch site that is well known and well loved, and there's lots of information about how to get out there and do it safely and responsibly. And so I thought that I would be able to definitely do it from BlackRock. And now I'm basically risking it all on a coin flip. And that's a little bit different. That's like one of the 3 big challenges. And like, yeah, so it's not my favorite answer. And if somebody has 8 square miles and is like, hey, you should do a launch from my property, we can like do the paperwork tomorrow. Then like it would be extremely hard for me to say no. But that's what it's going to take. And again, like this is kind of my own fault because I spent, the last 3 months like making the movie, which I'm extremely proud of. Like I'm so glad I got to make that movie. Anyway, kind of anticlimactic. Oh, what's this? Oh yeah, leap of faith. And the last thing is a giant thank you to everybody who helped me with this project, especially the folks that drove out to BlackRock. Zyla and Joe especially have been part of this from the very, very beginning, from the first test flights all the way through. These projects do not happen alone. This project would not have happened without probably like 20 people helping me in various amounts. Some people showed up for 1 hour. Some people drove down to BlackRock, and every single hour was important for this project. So thank you again to all of them. This is the end of the presentation. I'm going to go through the Q&A as fast as I can. Frank D'Angelo, what up? Hey, what's going on? Dave Graper, yep, seeing the total eclipse is incredible. Was I part of the MIT team Fin Flutter rocket launch in Maine, tree recovery with a very friendly neighbor? I was not part of that launch. I did hear about it though. That was probably a year or 2 before I showed up. Did I analyze the altitude in OpenRocket or RAS Aero? I analyzed in RAS Aero. I used OpenRocket for mass properties because it's really convenient to put really convenient to place the parts and like figure out how long the tubes need to be in OpenRocket. But once I got the mass properties and the CGs and excuse me, in the CGs and like an estimate of the fin size. I put that into RAS-Aero. That's where that 90,000 feet came from. I actually specifically omitted the altitude estimate from OpenRocket because the OpenRocket estimate was 100,000 feet instead of 90,000 feet. But I also have the RAS-Aero data that says 90,000 feet. Frank D'Angelo, again, hey, good to see you too. All right, I have now gone 7 minutes over time. I'm going to scroll through the chat to see if I missed any questions. Thank you all for coming. It's lovely to see you. Thank you, Todd, for helping me get this presentation back on the rails partway through. And let's see, did I forget? Oh, Robin asked about cameras. If you're still here, what I did to mount the 360 cameras, I put a microfiber cloth inside of a deployment bag, and I originally had this bow set up where I like clamshelled the cameras inside like a hard box, but even that like allowed some soot in because it had to have a seam for the clamshell to open. So I ended up figuring out how to do Bluetooth to turn on the cameras, and then I wrapped them up in this microfiber cloth. So that way I didn't have to like access the power buttons from the side, which half worked, exactly half, because one of them worked on the pad and one of them didn't, because we also had an Insta360 on the ground. David, they're the Insta360 X3. The X3 model in particular, it's nice and self-contained, and if you flip one of them upside down, you can fit two of them in the you can fit two of them in a 3-inch diameter rocket, which was extremely convenient. But yeah, that is what I ended up doing for the 360 cameras. I also had two radial cameras on the sustainer that I like catted up some like radial mounts. So they basically attached to like the side of the body tube. And that was important because the threaded rod for the motor went right behind these cameras. And then in the booster, there was an up-down camera on one side. And that up-down camera was a design that was iterated from, like, I think from that first stage test. It was a design that Joe uses a lot. Yeah. Siva Van Gool. Oh, that's pretty sweet. So in the most recent edition of OpenRocket, you can export straight to RAS-Aero. How convenient. I'm going to definitely use that in the future. There, it looks like there's one more question, perhaps. How's your day going? It's going great. I'm about to go. I woke up early and I'm going to go grab my breakfast and coffee now. I pulled together some of these slides at the last minute. But apparently I had too much material. Yeah, so if you, Jack, yeah, I'm hoping to get, the recording should be up on NAR's website. I'm also hoping to repost it to my channel if they are gracious enough to let me. And yeah, that's it. So at this point, I'm going to stick around for a few minutes to make sure I catch any additional questions in the chat. And y'all should go enjoy the rest of Narcon. Thanks for sticking around extra time. I'll stick around for like a minute or two, but I'm done talking. Thanks, Joe. Thanks, Jack. Okay, I'm not seeing any more questions, so I'm going to stop the broadcast. Oh, what's your YouTube page? Great, thank you, Robin. I definitely should have posted that. Ba, 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 ba. This is the movie, and here is the Great. Okay, the delay is longer than I thought, so I'll stick around a little longer too. Oh, and did I start rocketry before or after college? I started before college. I was lucky enough to join. I don't know if Jim is still in here. I was lucky enough to join a team in high school. I did 2 years. Got junior L1, my final year of high school. In case, can I see who is still here? No, I cannot. Oh, great. Hi, Jim. I keep going back and forth between the Q&A and the chat, and so I keep missing stuff. Going back to chat. Me. What's up, Nicholas? Just gonna type in the answers to these questions. Arrow for mock, or for planning the route. Oh, cool. That sounds like a fun project, Jim. There's another question. Ariane, I'm not sure if you meant your question to be private. I feel like I don't see any personal information in here, so I feel like would it be okay for me to talk about it in the just out loud, or would you rather I just type an answer? While I wait for that, does the aerodynamics change the tone when flying Mach 1? It does. So when you go Mach 1, you develop a bow shock on the nose cone, and then okay, cool. I'll answer yours next then, Ariane. Yeah, so when you go Mach 1, you develop a bow shock on the nose cone, because that's what's literally like the air. Yeah, so you develop a bow shock on the nose cone, and that causes your CP to shift forward, so once you go above Mach 1, instead of like usually, right, when you're burning a rocket motor, your stability is increasing because your CG moves closer and closer to the nose. The problem when you go above Mach 1 is now your CG is shifting, but your CP is shifting as well. And so making sure that you capture that CP movement in addition to the CG is very important. And it also gets extra interesting when you have 2 stages, because and you stage supersonic, because not only do you have the shock, if you have two different diameters, you have a shock at the transition, but then when you actually separate, there's like that area of low pressure behind the sustainer is extra dynamic because of the shocks at the back of the rocket. So if you're doing stuff at if you're trying to stage faster than Mach 1, it's important to make sure that either A, if you have different diameters, you have enough separation force, which really it's really hard to estimate. So strategy B is to make sure you have a pretty strong separation charge, or like separation force, so that way you just the transients that happen right when the two stages separate and air can like flow in between the two stages, those transients last a very short amount of time, and then the rocket can correct. Ariane asked, so would it also be that the force of the end motor pushing on the bent sustainer made the sustainer push back on the booster with enough force to buckle the staging coupler? If so, what would the breaking point for motors be? It could have shattered the staging coupler. I don't think that's what happened. Just looking at the video, it's pretty clear to me that it broke at the sustainer fin can first. Just judging on like where on you can like physically see on the rocket like where it breaks. That was a question. Oh, maybe you're talking about the staging bulkhead, where the sustainer sits on top of the booster. That one, the staging bulkhead, I haven't closed out yet. That could have failed first, and then that would have allowed the sustainer to move around more. The only physical evidence I saw of that was, well, it was shattered when we found it. So we like found little 3D printed pieces scattered around the desert, that were clearly from the staging bulkhead because they were the right color. But yeah, I don't really know. The staging bulkhead could have failed first. We didn't see it in the we did not see anything in the accelerometers. So what I did check was the flight computer from the sustainer and the booster did not show an event where like their position changed relative to each other. That would have been pretty hard to detect relative to everything else that was happening. But I would have expected like a sudden shift in acceleration in the sustainer in particular, and we didn't see that. I did do a calc on the bolts for that section to make sure that the bolts wouldn't break. The bolts in the staging bulkhead wouldn't break. But I am not sure if the staging bulkhead broke first and that led to the sustainer being able to shift more within the rocket. That is plausible, but I think it's unlikely. At least that's where I am right now. If I find something else out, I might change my answer. Jim Kane, what is the Hot Nozzle Society about? The Hot Nozzle Society, I haven't been in HNS for like a solid year. The Hot Nozzle Society is about bringing more people into rocketry. Ariane, that's totally okay. It's about bringing more people into rocketry and like changing the demographics within rocketry. Rocketry doesn't always feel like a safe place for women and gender minorities and people of color. I've been pretty lucky in my life that like rocketry is usually a safe place for me, but that's not always the case for other people. And HNS hopes to bridge that gap. And I haven't been a part of it for a while, but it's been especially helpful because a lot of rocketry is full of older folks, and there's also a lot of rocketry full of younger folks. And HNS and NAR in particular have established a pretty strong rapport to try and bring more people into the NAR like system, and like junior board members on NAR is something that I think HNS has been rallying for a lot. And then NAR is also like learning how to learning how to like interact with younger people and like people not like themselves, which is not easy. And so that's to me, that's what HNS meant to me. But I'm sure they have more information on their website about where they're at right now. Okay, I have, let's see. Okay, y'all. I think I've answered at least one question from all of you now. So at this point, I'm going to grab my breakfast and I'm going to go make some coffee. Thank you so much for sticking around. I really, really appreciate it. And good luck in your rocketry endeavors. And we'll see you next time. Yeah, the time and money to spend on rocketry is a big part of it. And I think having junior members attend NARCon for free may have been something that HNS helped with. Maybe, I don't really know. Yeah, all right, for real this time. See ya.